So the next thing we're going to move into here is talking about more complicated circuits. All right, so most circuits are a little bit more complicated than just a single battery and a single resistor. We're not going to really deal with circuits that have multiple batteries, although that is something that if you take AP next year you will talk about. However, we are going to talk about circuits that have multiple resistors like this one here. Okay, and so where we're going to start here is we're going to talk about the basic rules for current and voltage and how those work in a more complicated circuit. Let's start by talking about voltage or electric potential in complex circuits. So for electric potential, for voltage, we're worried about loops, okay? Because our rule that's going to govern how voltage works is in every loop, all right, the sum of the voltages must equal the voltage of the power supply, okay? Or the voltage of the battery, whatever is creating power to our circuit. So let's take a look at what we mean by this. So I'm going to think about some loop, some pathway through the circuit. So let's start here. We'll start on one side of the battery. That yellow there is one possible pathway through our circuit. And we see that our power supply is 10 volts, okay, supplying 10 volts of potential to our circuit. And the voltage across this resistor, the only resistor we hit, is 10 volts. So for that particular loop, the sum of the voltages across the resistors equals the power supply. And that one's easy because it's only a single resistor, but let's look at another loop. So let's imagine this red pathway here through the circuit, okay? And if we look once again at the sum of the voltages across the power supplies, we have 5 volts plus 2 volts is 7 volts plus 3 volts adds up to 10. Okay, so we can see that the sum of the voltages, 5 plus 2 plus 3, equals 10 volts, which is the voltage of our power supply. Let's try our one final pathway, which would be this blue pathway here through the circuit, okay? And we'll take the other resistor there. And what ends up happening there is, once again, we have our voltages add up to the voltage of our power supply. So we have 5 volts plus 2 volts plus 3 volts equals 10 volts, which is the voltage of our power supply. So that's how that rule works. The sum of the voltages for any loop must equal the voltage of the power supply. Okay. Two things to notice. All right. The first is when the circuit splits, the voltage drop across each branch must be the same. Okay, and we see that here with these two branches. All right, the circuit splits, and whether you go this way or this way, the voltage drop across each branch is the same, 2 volts. There's an analogy we're going to use, and I'll explain that on the next slide, that I think helps. But the way I think of it is we treat voltage like height. Okay, so I imagine the battery lifts the electrons up to a height. It's like an elevator for the electrons. And then in order to get to the other side, okay, they have to lose all that height to get back to the bottom. All right, so we'll look at that on the next slide. So I like to think of batteries like an elevator for electrons. So this elevator takes them up to some height, okay, and that's what the voltage is like. So we'll say it takes them up to a height of 10 volts. So the electrons go in this elevator, the battery, up to a height of 10 volts, okay, and then they go through the circuit, and as they go across various resistors, they lose that height. And what ends up happening is whatever height they start with, in this case 10 volts, they have to lose all of that height as they go through the circuit, as they go back down to the bottom. Okay, and so what we see is no matter what pathway they take, and we have a few different possible pathways here. We have this pathway, we have this pathway, and we have this pathway, and this corresponds with our circuit on the previous page. No matter what pathway we take, we have to lose all 10 volts that we started with. All right, and so we see things like when the path splits here and then eventually comes back together at this point here, all right, no matter which path we take, this one or this one, we lose the same amount of voltage, 2 volts. We lose the same amount of height going either way because the path comes back together. We have to lose the same amount. All right? So that's how I think of voltage. All right? We think of voltage like height. The battery lifts electrons up to some height, and they need to lose all of that height as they go through the circuit. Let's go ahead and do a practice problem. The first thing I'm going to do is I'm going to think about all my possible pathways through my circuit. So there's one possible pathway, that blue there. Another possible pathway is going to be this green loop here going through the middle portion. And then finally, I have this purple one going all the way around the outside. So those are my 3 possible paths through my circuit. And for each one, I know that the voltage has to add up to the voltage of the battery, which is 30 volts here. So I'm going to start with that purple pathway, that one on the way outside. And what we have for that one, as we go around, we have 17 volts, 4 volts, and then a blank here. So 17 volts plus 4 volts plus this missing resistor that we see right here. That has to add up to 30 volts. And so if I go ahead and do my math, I find that this missing one here is going to just be 9 volts. Okay, then I'm going to use my blue path. All right, thinking about this one here. And so for that one, we have some blank resistor there. We don't know the voltage on that one. Plus 11 volts, plus 4 volts, plus 9 volts, and that has to add up to 30 as well. Okay, and so that missing resistor there has got to be 6 volts. That's what fills in and adds it up to 30. And then finally, I think about this green pathway here. Okay, same basic idea. I have 6 volts plus a blank one plus 4 volts plus 9 volts. That needs to add up to 30. And so this missing resistor here has got to be 11 volts. All right. One quick thing to note here, I see that each one of these branches has a total of 17 volts. Okay, the circuit splits. We have 3 possible pathways through it from that point. All right, and they all end up being 17 volts, which makes sense because it all comes back together here. So no matter which path we take, this one, the middle one, or the far one, in order to come back together, we have to lose the same amount of voltage across each. Okay, but here we are applying that loop rule. Every loop must add up to 30 volts, the voltage of the battery. All right, once again, we have another voltage one, so I'm going to start by thinking about all my possible pathways through this circuit. Okay, so I have that one, I have that one, I can go through the middle branch here, or I can go through the 2 far branches, and I have 2 options when I get all the way out there of how I go about that split. All right, so there are all my possible pathways. And so what I'm going to do is I'm going to start, I'm actually going to start with the red one here and use that to figure out some of my unknown voltages. So for that red one, we have 8 volts, plus we have 6 volts, plus that missing one, and that has to add to 15 volts. So that means this missing one here is going to just be 1 volt. I can move on to my yellow one then, and so I'm going to have a missing plus 6 volts plus 1 volt, adding up to 15 volts, and so that means this missing one here must be 8 volts. I see here how those 2 parallel branches are the same. That makes sense. Moving on to the blue loop here, we have 2 volts plus a missing one, plus 6 volts plus 1 volt must add up to 15 volts. So that means this missing one here must be 6 volts. I see once again this branch is 8, which makes sense, as is this branch and this branch. Moving on to that green loop there, okay, I'm going to have 3 volts plus a missing one plus 6 volts plus 1 volt. So that means this missing one here must be 5 volts. And same thing for the purple one. The math works out the same. We see here how these 2 parallel branches, when it splits, it comes back together, end up being the same voltage. All right, moving on here to current, our rule for current, we're worried about junctions is the key thing here. So current splits when it goes into junctions, and what we know is that the total current going into a junction must equal the total current going out of that junction. Okay, so what we think about for that is we're going to look at these points here, all right, where the circuit splits. So we have 25 amps, it tells us, are leaving the battery, so 25 amps are going to be flowing like that. The circuit then splits. Some is going to go that way, some is going to go that way. We see that 10 amps goes through this resistor, which means there must be 10 amps of current going to the right. 15 amps goes through this resistor, which means there must be 15 amps going to the left. So that's an example of it splitting at a junction. That 10 then comes into this junction. All right, so we have 10 amps going into this junction, and it splits into 7 amps for that resistor and 3 amps for that resistor. And then we have another junction here, and so in this case we have 7 amps coming from that branch, 3 amps coming from that branch, combining to be 10 amps once again. And then finally, we could say there's 10 amps coming from here, 15 amps coming from here, and those two combine at that junction to be 25 amps. So with current, we're worried about junctions. Whatever current goes into a junction is the current that leaves the junction, okay? What ends up happening is when resistors are one right after another, the current must be the same through both, okay? And that's simply because if it goes through one, it has to continue through the other unless there's a junction for it to split. Okay, otherwise that current is just going to continue. Because current really is just like the flow of electrons, right? Electrons aren't going to disappear unless they hit a junction like this where they split and have two different options, two different pathways to go through. Electrons, I think about a lot like traffic, okay, or the flow of people, traffic, whatever, through various pathways, through different branches, right? And so that's going to be our useful analogy for thinking about current, and we'll look at that on the next slide. But the key rule here is right here. The total current going into a junction must equal the total current going out of it. So here is our analogy for current, right? We're thinking about it like the flow of electrons or traffic or even people. So in this particular circuit, we start with 25 people, all right, 25 amps at the top of the mountain coming out of the battery. Some goes one way, some goes the other way. And what we end up seeing is that if 15 go this way, 10 must go that way because it splits. However many go into, however many we started with, have to be however many leave. We're not going to have people or electrons just disappearing. So 10 go this way, it splits again into 7 and 3, okay, then it comes back together, those 7 and 3 recombine to be 10. If we follow the other branch, 15 go past this point here, 15 would still be flowing past this point here because there are no junctions, there are no splits, so that current just continues on. So let's do a practice problem with this, thinking about our current. So I'm going to start here with the fact that there are 11 amps of current flowing through this resistor here. I know that those 11 amps then have to continue on through that resistor. There's nowhere for that current to go, so that must be 11 amps. Then continues on around here and gets to this junction. All right, so we know we have 11 amps flowing through it, again, because that current just has nowhere to go. It's going to continue around our circuit. 11 amps is flowing into that junction. Some is going to go this way, some is going to go that way. I know that I have 3 amps going this way because I see down here 3 amps flows through this circuit, all right? So that means 3 amps must also pass through that resistor, all right? And again, the only way for the current to get to this resistor, for these 3 amps to get to that resistor, is they had to have passed through this resistor first. So that means if 3 amps flows through here, 3 amps must have flowed through there. And therefore, 8 amps went straight. Okay, because the current going in this junction was 11, we need to have 8 amps of current leaving that junction. We then arrive at our next junction here where 8 amps is going in. It splits once again. Some's going to go down. We see that 5 amps is the amount that's going down. The rest will go straight, and so it must be 3 amps that is going straight because 8 amps went into that junction. And so that 5 amps continues on down this branch through the first resistor, must continue on to the second resistor, all right? And then in the other one, that 3 amps continues on around this corner and through that resistor. So this resistor here gets 3 amps of current, all right? That would continue on. We could recombine these, so 3 amps is going here, 5 amps is going here. That's going to recombine to be 8 amps. All right, and then we have one last combination here. So we have 8 amps coming in from here, 3 amps coming down. That's going to recombine, and that's going to give us our 11 amps that we have that eventually continues on around. So we see here the current splitting at junctions. That's the key idea. We also see that when resistors are one right after another, they're going to have the same current because there's nowhere for that current to go. Let's work through this next practice problem here. I'm first going to fill in the easy one, and again, we're thinking about junctions here, but I do see that there's 2 resistors in a row, no junctions in between, so if 1.2 amps flows through this one resistor, okay, that means we must have 1.2 amps continuing on through that other resistor, so this one here is going to be 1.2 amps. I'm then going to start looking at some junctions. I'm actually going to start with this junction out here. I know that 0.9 amps is going to flow into that junction. It's going to split. 0.3 amps goes this way, which means the remainder, 0.6 amps, must go the other way. Okay? Those two are then going to recombine, those 0.3 amps and 0.6 amps, and we're going to end up with 0.9 amps once again flowing through that bottom part of our resistor. Let's continue with that and look at this junction here. Okay, so the 0.9 amps is coming in from the right, 1.2 amps is coming in from up top. That's going to combine to be 2.1 amps flowing through that portion of the circuit. Let's keep going, looking at some of our junctions combining here. So I'm going to look at this junction here. We have 2.5 amps coming from the one side, 1 amp coming from the other side, so that must combine to be 3.5 amps. And then when those two combine, right here, the 2.1 and 3.5, I'm going to end up getting here 5.6 amps going this way. So that 5.6 amps is going to flow through that first resistor there, so that'll be 5.6 amps. It's then going to continue on to that next resistor, nowhere to go because there's no junctions. So that one must have 5.6 amps as well. We've now filled in all of the things, but let's just continue thinking about how that splits up and make sure everything still works. So we have 5.6 flowing through the battery, ultimately leaving. 3.5 amps goes this way. And 2.1 amps goes that way. That 3.5 splits into 2.5 amps and 1 amp. That 2.1 goes straight, and then we reach this final junction here. 1.2 goes down. The remaining 0.9 amps goes straight, and it all works. Okay, so we're focused on junctions here and focused on situations where it's one right after another.